In the last video, I introduced Grover's search algorithm using reflection operators. In this video, I'm going to explain how to simulate Grover algorithm on Qiskit. So I will show how to implement the oracle and also the Grover reflection operator that we saw in the last video. So before I get to Qiskit, where I have already implemented the code, and you can download the Jupyter notebooks that I will show from the GitHub URL that I have given in the detail of this video. So, but before I show the Jupyter notebook, let me briefly describe the implementation gates that are required for the oracle and the reflection operator. So for that, let's go to the nodes. Okay, so we are going to be simulating Grover algorithm on Qiskit, the latest version of the Qiskit 1.x. And let me first recall what are the steps that are needed. So we had the algorithm like this. There were header marks on all the qubits, and all qubits were initialized in zero state. And as an example, actually, let me stick to one specific number of qubits. Let's say we take 3 qubits, and you can easily generalize to higher number of qubits. There is this oracle UF that marks a particular state, and then there is this layer of header mark that is part of the Grover reflection operator, and then there is this function U naught, and then header marks, and then there are measurements after R repetition. And then the measurements. So first let's see how to compute R. So R we found was to be computed as 4 pi over 4 alpha minus half, where alpha was sine inverse 1 over n square root. So in the present case, if number of bits are 3, then n would be 2 power 3 is equal to 8. Okay, and then we can apply the ceiling function, actually flooring function on R. So if let's say R comes out to be 3.4, we will take R to be its integer part. So we will select only 3. Now let's come to how to implement UF. So if you recall, UF has to work like this, that it gives positive sign to all states except the state that is the solution that we are looking for. For example, if I'm going to search for an item with an index, let's say 101, so it should be giving a negative sign only when the input to this oracle is this cat 101. So we can easily implement such an oracle like this. So the UF circuit can be like this, and then I can have a Z gate here. So this is like a multi-control Z gate. So when this line is 1 and when this is 0, this Z gate will be active and it will when this is 1, then Z gate will give it minus sign. So this means that if the input is 101, the output would be minus 101, and for all other inputs, X will go to X, because either the Z gate will not be active, or if the input here is 0, then the Z gate will not give it a positive sign. Now in Qiskit, it's a little bit harder to implement this multi-controlled Z gate. We can easily implement multi-control X gate. So for that purpose, what we can actually do is that use this fact that Z gate can be written as Hadamard X Hadamard. So with this, I can actually implement this gate like this. So let's put an X gate here, and then a Hadamard here and a Hadamard here to simulate Z. So this circuit is the same as this circuit, except that the Z gate is implemented using an control X gate, and the X gate is converted to the Z gate with Hadamard X Hadamard. So this is essentially equal to control C. So this circuit can implement this oracle if we are going to mark state 101 with minus sign. If we have some other state, then these control gates would change. Now we also need to see how to implement U naught. So U naught was defined like this, that it was this operation that it gives a negative sign to every state except 0 state. Okay, so but instead of this, it's actually better to implement minus U naught. The reason is this, that implementing this gate requires a lot of gate, and that will introduce a lot of errors into computation when we run an IBM quantum computer. And replacing U naught with minus U naught wouldn't do anything to the circuit, because this minus is only a global phase, because this minus is multiplying the total state of all 3 qubits. So at the end, it wouldn't impact the measurement statistics. So instead of implementing U, let's implement U naught. Now that is easier, because minus U naught is I minus 200. So this is just a gate that I can expand like this: minus 1 0 0 0 0 1, and so on, because it's just from identity I have to deduct this operator. So let me just show. So this identity is, let's say, for 3 qubit case, it would be an 8 by 8 matrix, and this 0 0 would be this matrix. So 1 minus 2 over here will give us minus, and everything else is 1. All right, so let's implement minus U naught gate, and it's also like similar to UF, but now we have fixed the state that we are going to mark with 0. So for 3 qubit, this 0 state is this state that we have to give a minus sign to. So this would can be implemented using Z gates like this. So this circuit when the input over here is 0 and 0, so these controls would be activated and the Z gate would be applied. And then when the input is 0 here, this X gate will make it 1, and the Z gate will make this 1 as -1, and the X will convert it back to -0, 0. So overall, the 0, 0 state will go to -0, 0, 0. And for every other input, if these combination is different, then the Z gate will not be activated, so no phase. And if this is 0, 0 but 1 comes here, then this 1 becomes 0, and Z gate will convert 0 into 0, no minus sign, and then this 0 will be converted to 1. So even when this is activated but there's 1 here, we will still get positive 1. So we are getting the minus sign only when all three inputs over here are 0, if we have this circuit. And again, as we just saw previously, that this multi-control Z is a little bit difficult in Qiskit. So we can replace this Z gate with the let me just take this little bit over here and draw the equivalent circuit using the control X gate. So I have to have X gate here, and the control Z would be Hadamard X, Hadamard, and then X gates again. So this comes here. So this gate, this is equivalent to this, and this will work as minus U naught operator that we have to implement in Qiskit. Okay, so let's see its application in Qiskit. And this, this activation for 0 state is possible in Qiskit as well. But if you want to use the activation with only when the state is 1, you can replace this circle with an X gate dot X gate if you like. Okay, so let me show the implementation on Qiskit. So let's go to alright, so let me walk you through to the circuit that I have implemented. So essentially I have this UF implemented for this 3-qubit circuit, and this is a for state 101, and you can see that this 1 and 0, I specified it with this 1 and 0. Remember, indexing in Qiskit starts from the right, like this top qubit Q0 is coming on the right side over here. So with this multi-control X gate, we are able to create this circuit that will work as an oracle to give a minus sign for state 101. Now, since this is an oracle that I will have to use many time in the circuit, I'm putting this inside this function. So I have defined a function called phase oracle, which is taking the quantum circuit as input and number of qubit as input, and giving me this circuit as an this QC as an output, because it's just adding these Hadamard multi-control X and Hadamard to the circuit. And then this is the circuit for the minus U naught operator. So you see the activation is now 0, 0, and then this is just simply the Z gate applying to Z gate setup so that it gives a minus sign for 0 state input. And again, I'm putting this in an operator which I'm calling diffuser for historical reason. Grover refraction operator is also called diffuser. So I'm putting all of this circuit that I'm showing here just for the showing purpose here inside this function diffuser, because then I can call it inside the circuit when I'm repeating. Okay, so this is the main part of the circuit. Here I have like these 3-qubit, and then this is the circuit initialization, and this is number of solution is 1, since we are only working with the one solution. And this is where I'm computing alpha, and from alpha this is how I'm computing this number r, and I'm simply rounding it off instead of using the floating function. So the alpha r would be rounded off to the nearest integer here. And then you see the first part of the code is Hadamard to all the qubits. So this is just this Hadamard that you see here. So this is this Hadamard, and then uh, after this I'm just repeating the circuit with 2 units. So there is a phase oracle which was UF, and this diffuser which I was calling V operator. So just I'm repeating it R times, and then at the end I just have this Meyer operator. Okay, so you can see the circuit repeating 2 times. So R has been rounded off to a value of 2, and then there is this measurement at the end. And now I submitted the job to the simulator, and here I'm using basic simulator, but you can also use air simulator as we have done in the previous notebooks. And you see the state 101 that was marked by the UF operator, it's showing up with a very high probability as expected. And then I submitted this job to IBM quantum computer, IBM Kaiv, uh, and then the results are still showing a pretty good result. Like this 101 state is coming with high probability, even though the noise in quantum computer is giving other states with non-zero probability as well. Okay, so just to one more thing, and that is that you can actually implement, you can use something another function from the from Qiskit, which is dot append. So instead of using the way that we used here, where I just call the phase oracle function as it is, so instead of this, where we see the internals of the circuit, if you use dot append command and then append the phase oracle here, and then give the range of the qubit where you want to append the circle, we can get a very nice repetitive pattern of circuit, which is little bit easier to understand. So this is the first Hadamard layer, this is UFV, and so on. So this is a diffuser V, and this is the phase oracle. And with dot append command, I don't see the internals of the circuit, I just see a box, and the internals are hidden from us. So this is just another one nice feature if you want to see the block structure of the circuit. So after this, it's the same thing. You can submit to simulator and get the results, and you can submit to, let's say, IBM quantum computer and get the results like that. Okay, so this concludes our introduction to the implementation of Grover algorithm on Qiskit.